All right. So we'll move on to the next topic, which is Coulomb's law. Oh, crap. Wow. Okay, give me 1 second. There we go. Okay. So we'll just briefly talk about these 4 topics, and I have 2 examples at the end to follow up with. As for a brief history of Coulomb's law, I do believe the guy's name was Charles Coulomb, that developed this idea and sort of investigated how charges worked. So essentially, it was sort of known that electric forces increase when objects have either more charge or when charges are moved closer together. Okay, so there's this magnitude idea of a little charge, little q, versus a much bigger charge, big Q. That's going to change your electric force or your distance. So having things close together or having things further apart, we know these two things sort of affect this force that these two charged particles will feel. And then on the flip side, if you decrease the magnitude of the charges, or if the charges are moved really far away from each other, then that electric force also decreases. So there's clearly 2 different things that you can change that will cause these particles to experience greater or less force. So this force law is known as Coulomb's law. And Coulomb actually used a torsion balance to measure this electrical force. This is the same method that was used to determine the gravitational constant. So if you remember from Physics 1, I believe we only talked about it briefly, but essentially if you have 2 massive bodies like out in space, and they both have their own separate masses, m1, m2, you can actually calculate the force of gravity, that attractive force between them, essentially just by the force due to gravity is big G times m1, m2 over r squared. So this setup, this gravitational setup, was actually determined using a setup similar to this. So this is a torsion balance. Oh, I forgot who it was, but this torsion balance was originally used to measure changed colors. This torsion balance was originally used to measure this value here, G, in this equation for gravity, but Coulomb had the bright idea to sort of set up the same approach and use it to actually measure the charge constant, or at least use it to investigate these attractive properties and repulsive properties among charged particles. So what Coulomb discovered is that the electric force obeys the inverse square law, just like Newton's law of gravity. And I believe we've talked about that back in Physics 1. So essentially gravity and the electrostatic force, Coulomb's law, both of these have this 1 over r squared feature in their equations. So gravity has it, Coulomb's law has it. We'll actually write out Coulomb's law in just a second. All right, now we can actually put some math in here. So if 2 charged particles, one of charge Q1 and the other of Q2, are a distance r apart, then these particles are going to exert a force on each other. And the magnitude of that force can be calculated with this equation right here. Okay, now instead of like that big G in gravity, we actually have K, which is the electrostatic constant. These forces are an action-reaction pair, as most force interactions are. You'll remember that from Physics 1. And that's sort of represented here in the math. So whatever force is happening from the first charge on the second, that's going to be essentially an equal and opposite force that's happening from the second charge onto the first. So the forces are directed along the line that joins the two particles. That makes sense. Path of least resistance kind of thing. Your shortest distance between these two things is the direction that the forces are going to act on. One big key thing to remember here is that the forces are repulsive for like charges. They're similar, they don't want to be around each other, and then attractive for opposite charges. Okay, so they're different. They want to get closer together. So we have some figures here that are useful. We have two positive charges, so you'll notice we have Q1, Q2. Now, Q1 is wanting to, I'm going to change my colors. Q1 is wanting to push Q2 away. Okay, so this is our 1 on 2. And then Q2 wants to push Q1 away. So this is our force of 2 on 1. Similarly, we can change these charges from Q1 to Q2. We could make them negative. We could do this for 2 electrons if we wanted to. So that means we have same thing again. We have this repulsive force, 1 on 2, and then Q1 here is being affected by Q2. So this is going to be Q2 on 1. Now, if we switch these and have opposite charges, if we have like an electron and a proton here, or just anything of similar size, or as long as the charges are the same, Q1, Q2, but opposite in magnitude. So here you'll notice that the vectors are flipped. So now we have this negative Q1 particle is trying to, it wants to attract this positive charge. So now you'll notice the vectors flipped in the opposite direction. So this is our negative first particle trying to attract the positive second particle. And then same thing going the other way. Here you'll see we have this positive charge wanting to attract this negative charge here. So it's going to be the second positive charge working on the first negative charge. So Coulomb's law essentially describes the force between these charged particles. Generally, we're going to talk about these as point charges. A charged particle essentially has a mass but no size. Okay, so this is just a simplification. It's just like back in when we were doing kinematics, and we had the all the examples of like we have a car moving, but we're just going to model it as a point particle because the shape doesn't matter. Okay, so in this case, this has got to be something that's small and compact enough to just be represented by a point on the page. And that's essentially where Coulomb's law is. It works best is when you're thinking about things in terms of point particles. Now, Q can be either positive or negative. We've seen that. Given the absolute value signs in Coulomb's law, so like when we write out those charges, it always looks like this, Q1, Q2 with absolute value signs. So the first part of Coulomb's law only gives the magnitude of that force, okay? It's going to always be a positive number. The second part, which is up to you, uh-oh. The second part will, ooh, give me one moment. I seem to have lost my camera, but it's fine. The second part of the law, that you have to decide. You get to decide whether interactions are positive or negative. So anytime you use Coulomb's law, that's a sort of like a two-step process. You get the size of the force, but then you have to step in and decide which direction it's going to be. So we also have this force, we need to come up with a way to describe it in terms of units, right? So the SI unit of charge, which is the Coulomb. Okay, so when we talk about things that are charged, we're talking about it in terms of Coulomb. This is derived from current, which we'll talk about later, so that's no big deal. Okay, so now we have this charge that's acting on the particle, which eventually is going to give rise to a force. The fundamental unit of charge, which we talked about last time, which is on a proton or an electron, it actually, these things have a value of E, which I hate because that's also like Euler's number, you know, E to the X kind of thing. But in terms of electrostatics, E is actually just the fundamental unit of charge. This is the charge that an electron or a proton has. We've written it out previously like E negative for an electron, E positive for a proton. That actual value, which I promised last time we would get to, is actually 1.6 times 10 to the negative 19th coulombs. So this is actually a very small amount of charge. So it turns out electrons and protons are barely charged at all. It's a tiny, tiny amount. But once this fundamental unit of charge, once E is established, then you can use that torsion balance I showed you in the first slide. You can use that torsion balance to actually measure K, that electrostatic constant. So it turns out that the value of K is actually 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. So the units are really wild. So remember this, Newton meters squared per Coulomb squared. This is for K. Now, a lot of times in our calculations and what is totally fine to do on the homework, the problem sets, you can round this up to just 9 times 10 to the ninth. Unless you need something super specific, maybe like in a laboratory setting, just rounding this up to 9 is totally fine for everyday calculations. So we'll do that. There's no expectation to remember the 8.99 value out front. So in addition to this K, this electrostatic constant, we also have the permittivity constant, which is defined as epsilon naught. Okay, so this is epsilon here. Another Greek letter. So this is epsilon naught equals 1 over 4 pi k. Okay, here's our permittivity constant. The permittivity, you may hear it as like the permittivity of free space, and that's just essentially how well these, for now we'll call it essentially how well these forces will extend out and actually affect other particles. So that's essentially what this parameter here is. It's sort of just like a scaling factor. Sort of like a scaling factor for the force. It tells you essentially how it's seeping out to affect other charges. The same thing with the electrostatic constant K. It's just a scaling factor out front that tells you how well this relationship actually works, so to speak. But notice that we can actually rearrange the statement and actually get a new thing for K. So you'll notice, I'll switch my colors. K is down here in the denominator, but if we solve for K, we get this statement here. So we can actually just switch the place of the permittivity constant and the electrostatic constant, which means we can substitute K for this more gross statement here. We can rewrite Coulomb's law as F equals 1 over 4 pi epsilon naught times the multiplication of the charges over the distance squared. And it turns out this is sometimes helpful in the future to write it this way. Sometimes it's helpful to keep it old school and write it this way. It just depends on the situation. So just be aware that these two things are actually the same. Okay, now we know what Coulomb's law is. We know what the units are. It's a force. let's actually talk about how to use it. Okay, so Coulomb's law is indeed a force law, and forces are vectors. So we know we're going to have some sort of vector calculation in here. So there's essentially three important things to remember about Coulomb's law. So Coulomb's law applies only to point charges, right? So those little charges of some charge Q. Coulomb's law applies only to electrostatics, and electrostatics is essentially the assumption that the charges aren't moving. Okay, so stationary charges. So this Q up here is not moving. And then just like other forces, you can superimpose them, you can add them up. So if we had one particle, particle J here, and its charge, QJ, but then if we had a million other particles all around it, we could actually apply the law of superposition for these forces. Say, well, particle 1 on J exerts a force, particle 2 on J exerts a force, particle 3 on J exerts a force, and so on and so forth. So it is summative. You can add this up just like any other forces from like physics 1 when we were looking at gravity, friction, the normal force. They all just add up in the x and y directions pretty much. So as far as problem solving goes, I did include this from the book because it's important to remember all these steps. That'll keep you from going astray when you're solving these problems. Some of these can be pretty involved. So do take a look at this in the book as well. Take some time, make some notes. But the first thing you should always do when you solve any sort of physics problem is you want to take this modeling approach. And for electrostatics problems, you want to identify point charges or objects that can be modeled as point charges. Maybe you have a charged sphere, but you're so far away it sort of looks like a point particle to you. So maybe you're far enough away. Let's see, far enough. Okay, that should say enough. My bad. So far enough away to actually model this as a point particle. You could say, well, this thing's so far away and so tiny, we're just going to call it a point particle. That's the idea here. So once you identify what needs to be a point charge or a point particle, that's when you're going to draw your sketch. You're going to use a pictorial representation and establish a coordinate system. So maybe here I might say, well, my positive x direction is this way, positive y direction is up, so that means I'm in the negative y direction down here. Okay. Now, if you have other charges, you'll need to show the force vectors on those charges. So maybe I have a positive charge here, and then maybe I'm also holding a positive charge down here. Well, that means if I draw my vector, I know that I'm going to have a force pushing this sphere away because they're like charges. They want to repel each other. So now I've got my force vectors drawn in. Of course, they'll be right over the particle. We're going to assume that these particles are both on the y-axis. I just don't want to get my y-axis too cluttered when I draw it. And then, of course, you'll want to identify what the problem's trying to find. Okay, so maybe you want to, I don't know, we want to find this force up here, the force of, I'll call my particle 1. On the sphere can be particle 2. Maybe that's what we want to find. So once we identify this force that we're trying to find or this value, that's when we can jump into the mathematics. So now we can basically just say, well, this is a charged particle problem. So we know we're going to use Coulomb's law. So since we have the directions of the forces, we know that we've got two like charges. So they're going to repel each other. Of course, we can also do like graphical vector addition if we need to, and then write each force in, write each vector force in terms of its x and y components. So once you get this set up over here, let me switch colors yet again. Once you get your math set up, it becomes problems like we've done before in Physics 1. Once you get to here, you just sum your forces in the x direction, then you sum your forces in the y direction. You all have done this many times. There's nothing new. So really, the new thing here is just the setup of electrical forces. And once you do that, it's the same old mathematics, okay? Once you get to essentially here, everything below that, that's just math. Okay, so once you actually sum the forces and solve for what you're looking for, that's when you go back and check that you have the correct units. That's important. And then that you have a reasonable answer. Okay, if you have like, if the force you come up with as your final answer is, you know, tens of millions of newtons strong, and you're just looking at two charged particles, that's probably wrong. So do keep in mind you need to take a step back and make sure your final answers are on track with what you would expect them to be. So that being said, let's take a look at an example here. So we have two 10 nanocoulomb charged particles that are 2 centimeters apart on the x-axis. Okay. What is the net force on a 1 nanocoulomb particle placed halfway between them? Okay, we can draw that out. So here I have my two 10 nanocoulomb positive particles, 10 nanocoulombs, 10 nanocoulombs. You'll notice I drew a picture. Now I'm labeling it. And then we also have this smaller charge in the middle of just 1.0 nanocoulombs. All right, now we just need to figure out what the net force is. So that means we need to add up some forces here. We want to figure out what that net force is on that charge in the middle. So let's see, it looks like we have this first 10 nanocoulomb charge. Well, that's trying to push this smaller positively charged particle away. Then we also have this second charge, Q2, which is trying to push Q3 away. Okay, so we have these two force vectors, this green and this orange, and we need to sum these up. Okay, now it's going to look like Christmas, but let's see. Let's get rid of some of my markings so I can make this match up. So let's do the first one here, F1 on 3. Okay, I'll match up my colors. So it's going to be F1 on 3, so the force from Q1 on Q3. That's this one. Now, it's only in the y direction. Or sorry, it's only in the x direction. This is only an x hat. So we don't have to worry about components, right? Everything we calculate would just be in the x direction. Okay, well, let's go ahead and calculate that. So we have our Coulomb's law equation. This is pretty straightforward. We just need to know the value of this force, so we can just plug in the numbers to get it. So we have our electrostatic constant K. We have our Q1 and Q3. Okay, that's what we're looking at. Q3 is the charge in the middle. Then we have our distance. Okay, so these things are 2 centimeters apart total, which means their actual distance is just going to be 1 centimeter apart. We need to change that to meters to keep everything in SI units. And then when we turn the crank on this, you'll notice that we have Coulomb squared in the denominator. which is going to cancel out those coulombs. We have meters squared in the denominator, which cancels out that meters squared in the numerator, and that leaves us with just newtons. So 9 times 10 to the negative fourth newtons is what's being experienced here by that vector, the green vector. Now, if we look at the other vector here, so we have the force of 2. Okay, I'm labeling that the force of 2 on particle 3. So 2 on 3. Now we need to do this red vector. And it turns out we do the same thing again. We plug in these values. Here's our Coulomb's law. Plug in the values. And lo and behold, we get the same number again. Notice that they're both positive. But you'll remember, this is only the first half of Coulomb's law. We always get a positive answer from Coulomb's law. Always positive. Now we know we've got the numbers. We now have to decide if it's going to be a positive or negative when we add them together. So now we decide the signs. So I'll do this in blue. Okay, so we take our first value, the positive. We know it's positive, right? Because it's in the positive x direction. Right. So this is our green vector. Positive x direction. Now we need to include the next vector. The vector, the force vector 2 on 3. But now you'll notice that 2 on 3 is pointing in the negative x direction. Okay, so that means that negative sign there in the math becomes very important. So now we essentially have the same value, positive value minus same value. We know that's going to be 0. So it turns out that the net force on this particle in the middle is actually 0. It experiences no net force. So that particle in the middle is not going to move. It's going to be stationary because there's no forces acting on it. Wow. Acting. There we go. So I just have a note here. It says, look at the geometry, because the geometry, the way things are set up is why it's not moving. You have equal charges. They're both positive, and because they're one on each side of this particle of interest, that's what's causing the everything to cancel out. It's because of the geometry of the situation. Okay, so we have the geometry is what's causing this opposing situation and canceling out. Okay, let's look at one more example and then we will call it quits. So suppose we have 3 charged particles with Q1 of negative 50 nanocoulombs, Q2 of positive 50 nanocoulombs, and Q3 of 30 nanocoulombs, and all 3 are placed on the corners of a 5 by 10 centimeter rectangle. All right, so what is the net force on Q3 if this is the case? Well, what we're interested in is the net force acting on Q3, which is up here in the top left corner. Now we have a pictorial representation. Now that we have our pictorial representation, remember that the next thing to do would be to move to more of like a free body diagram where we can add vectors. So we want to add vectors, and I'll put in parentheses here, sort of like a free body diagram. Okay, well, let's think about where these vectors came from. So we know this is our particle of interest. We want to know what the net force on this thing is. Okay. Well, we have Q2 down here acting on it. So Q2 is also positive, right? Our particle of interest in red is also positive. We know they're going to repel. So Q2 wants to push Q3 away. That makes sense. But we also have this negative charge down here. Now, since this charge is negative and our charge of interest is positive, that means they're going to attract each other. They're different. They want to be together. So that means we have a vector actually going in the other direction. We actually have a vector that's trying to bring these two charges together. Now we can use geometry to think about what it's going to look like when we sum these two vectors together, because we want to add up F1 on 3 and we want to add up F2 on 3. We want to add those two things together. Okay, let's see, what would be a good color for this? Let's use green. Now, actually, I want to switch to blue. So F1 on 3, it doesn't have anything in the X direction. It's all in the Y direction. Okay, so there's no X hat information. Now, that's not the case with F2, right? Or F2 on 3, because F2 on 3 has a component here in the X direction. You can see that. So if we did F2 on 3, or the magnitude of it, so the length of that vector times cosine theta, that's going to give us F2 on 3's X component. Okay, so it does have an X component. F2 on 3 also has a Y component. I am running out of colors. So you can see that there's also this Y component, right? So we've got F2 on 3, which has an X and a Y component, and we have 1 on 3, which only has a Y component. Okay, this should be review. This is a breakdown of a free body diagram that we've done many times in Physics 1. So we need to add these things together, but we want to do it in component form. So we'll do it once for X's, once for Y's. So do notice how the components of these vectors make up F3, right? So we sort of drew that out. F3, which is here, it has to come over the same amount as all of the X information, but F2 on 3 is the only one with X information. So that's why it comes out to the negative X direction this far. And then we also have to have the Y component of this first vector added to the Y component of this second vector. So these two are sort of canceling each other out. You can tell that there's going to be a little in the Y direction left over, because if we take this amount of positive vector and subtract it from this amount of negative vector here, this little piece that's left, that's going to be your Y component here. Again, this should be review. All of this is covered extensively in Physics 1. All right, so now that being said, let's get these pieces here. Okay, so we're going to add F1 on 3 and 2 on 3, F1 on 3, F2 on 3. So now we need the individual components of F3. So I'm going to label it in blue here. This is the component, the vector that we're looking for the components of. Now, let's first determine, I'll do it in green, I suppose. Let's first determine the X component of this vector. So that means we know we want the X component of 1 on 3. That's this vector here, but, well, that has no X component. It's only in the Y direction. So this just goes to 0. We don't even care. All right, now we need the X component of 2 on 3. Okay, well, here is 2 on 3. And we know its components in the negative X direction, right? So here's the force, but only the X piece of it. So we know it's going to be in the negative X direction. I have my minus sign here in the math. So to get that x component, we just need to take the cosine of that angle. So the magnitude of f2 on 3 times, so the full length, the hypotenuse essentially times cosine, will give us the x component. Now we can do the same thing in the y direction. So I'll change this to red. So now we want the y direction. Well, we need the f1 on 3, the y component of that. And you'll remember that this whole thing is in the y direction. So we just want the length of the whole vector, right? So we don't have to scale it by a sine or a cosine. Okay, we know it's going to be in the negative direction as well, so we'll include the negative in the math. Now we just need the y component, 2 on 3. Okay, well, over here you can see that this is the y component. This is how much in the y direction f2 on 3 is going. Okay, so we know it's going to be positive, so I've got my plus sign here in the math. But we still need that magnitude. We have the length of the whole vector, f2 on 3, right? We know this part. We just need to scale it, so that's going to be a sine function, right? Because we want this piece here. We want to know what this component, this length is. So we're going to scale it with a sine function. Okay, so this is essentially saying the full length of f2 on 3 times sine will give us the y component. So therefore, we can actually write out f3 right now. We can actually write out this blue vector that we wanted all along. Okay, so switching back to blue for my blue vector here. So it turns out just in the x direction, we have the negative component of f2 on 3, right? So that's green. I should even label it as green. So this just comes from the negative component that's in the I hat or x hat direction, whichever you prefer. And then we need the y component in the j hat or y hat direction. Now that's the one where we actually have two terms. We have the full length of vector 1 on 3, and then we also have that scaled sine component of the other vector. So now we essentially have our answer. This is the force. This is the full vector f3, but we don't actually have any numbers yet. We've set it up, and this is a good approach to these kinds of problems. We want to set them up first, and then we want to fill in the numbers. Okay, so we know what our answer is going to look like. We just need to dump in these values. Okay, so let's figure out what f1 on 3 is, what f2 on 3 is, and what theta is. Well, these fortunately are really easy because this is just Coulomb's law now. That's what the only forces that we're considering. Okay, so let's do f1 on 3. And just as a reminder that it's going to be, here's our first particle, here's our third particle. Let me make sure I get this right. Yes. So f1 on 3, we want to figure out the magnitude of this vector. So we're just going to dump in values. We know what our electrostatic constant is. We have the charge of the first particle given to us in the problem. Looks like I don't have it on this page, but you should have written it down. So here's our Q1, Q2, here's our distance. It's 10 centimeters. We can figure that out simply from geometry. And then we can just plug and chug, and we get the magnitude. Remember, this is always going to give us a magnitude. It's not going to give us a direction because of the absolute value signs in Coulomb's law. Same thing again, Coulomb's law, electrostatic constant. This one's a little more tricky. So this is 2 on 3, right? So here's a little note. This is just the distance between 2 and 3. Since this is a diagonal across the rectangle, we need to use the Pythagorean theorem here. Squared plus b squared. Right, this is still just a distance calculation. We just didn't, that number wasn't given to us. We just have the 5 centimeter width, 10 centimeter height, but we needed to use the Pythagorean theorem here so we could actually get that distance across the rectangle, which I've labeled here in green. Okay, so we plug that in for our R value, and then we get this value here for the F2 on 3. So now we have the magnitudes. We know F2 on 3, we know F2 on 3, we know F1 on 3. Now all that's left is we just need to figure out what this theta is here in our equation. Okay, so note that theta does show up in two places. So you've got a theta here, you've got a theta here. So we can actually just use the sides of the rectangle given to us in the problem and determine the value of theta here. So we know that tangent from our old SOHCAHTOA, using tangents, that's going to be opposite over adjacent. Well, the opposite side here we know is 10 centimeters. We know the adjacent piece to this angle down here is 5 centimeters. Well, that gives us a ratio of 2. Okay, so if we have tan theta equals 2 when we simplify this, well, we just take the inverse tangent of both sides, boom, boom, and that gives us an angle of 63.43 degrees. So now we figured this out 2 slides ago. We just figured this out on the last slide, 2 slides ago, last slide, 2 slides ago. We now have all the pieces we need to actually just plug things in and just turn the crank at this point. So here's that magnitude we figured out, cosine of 63 degrees in the I hat or X hat direction. And then we have same value again, except we want the Y component, Y hat or J hat component of it. Okay, so it looks kind of gross, but really we're just going to plug in things and simplify. So this whole thing in the I hat direction simplifies to a number here. Everything in the J hat direction or Y hat direction simplifies to another number. Now we can rewrite this in scientific notation. That's going to give us these two components here. The negative 4.83 times 10 to the negative fourth newtons. Units are important. So that's how much force is in the X direction. Notice it's negative. That makes sense. We want it to be negative. And then we also have negative 3.84 times 10 to the fourth newton, negative fourth newtons in the Y direction. This is also negative, and that is exactly what we wanted, because you'll remember the force we were after, F3, actually was in the negative X direction and in the negative Y direction. So having two negative values here totally makes sense. If we wanted to find the magnitude and the direction of F3, we can also do that. We know that the magnitude or the length of any vector can be found by essentially, oops, these should have squares in them, by essentially squaring the components, adding them together, and then taking the square root. Okay, so we can do that from those values we just figured out. We'll square them, add them together, take the square root, and then it turns out the actual length, so how long this is 6.2 times 10 to the negative fourth newtons. Okay, and then to get the angle, so we can talk about where this vector is pointing because we can use the angle phi here. So to figure out angle phi, we can essentially just use the ratio again. It makes just a triangle, so the y component over the x component. And then we take the inverse tangent of that. That gives us roughly 38 degrees. So we could write our answer like this in component form, which is totally fine, or we could give it in terms of a magnitude and a direction. So we could actually also write F3 as a force of 6.2 times 10 to the negative fourth newtons at an angle of 38 degrees below the negative x-axis. And that pretty much sums up this vector as well. So you've got two options to write these out. Generally, I won't care which way unless I give you a specific in the problem set. But that's pretty much summed up Newton's law. Shoot, that's summed up Coulomb's law. And as always, if you have any questions, please let me know. And from here, we'll move on to actually start talking about electric fields.